So this fourth paper is going to be on an optimal any-angle pathfinding algorithm by Daniel Harabor and Alban Grastian.
Hi, so my name is Damir Harabor. This is joint work with Alban Grastian. We're both from NICTA and at the Australian National University. So just before I begin, I want to manage some expectations. I know this is ICAPS, where empiricism rules, but I want to tell you that you will not find any plots, charts, tables, or empirical comparisons of any kind in this talk. This is a theory paper. It's a somewhat unusual theory paper, also in that there will not be any Greek. I think that's a good thing. I have enough trouble with English. Okay, so the topic of the talk is pathfinding. You've heard lots of people introduce it. I won't bother to do it again. What I will say is that we're focusing on a particular variation of the pathfinding problem, which is where the world is represented as a square grid. We assume that there is uniform costs, and we assume, perhaps somewhat unusually in a grid domain, that the nodes of the graph are the vertices of the grid. So some people like to model the individual tiles as the nodes, and you'll see why we have to do this. So, two often cited criticisms about why you shouldn't pathfind on grids is, well, in the first case, when you compute a path and an agent starts to execute it, it looks really dumb, right? It can only turn at 90 degrees and 45 degrees. And also the length of the path, even if it's optimal with respect to the grid, it's not necessarily optimal. So if you weren't forced to go through the points of the grid, you might do better. And so we can see here, there's a path that's not respecting the points of the grid, which is shorter. And this, in a nutshell, is the any-angle pathfinding problem, okay? You're given a grid world, and the objective is to find the path which is shortest in the continuous space. So if this sounds familiar, perhaps it should. Any-angle pathfinding is a variation on the well-known continuous pathfinding in a two-dimensional plane. This kind of stuff has been thought about in the areas of robotics, for example, since the 1970s, using things like visibility graphs, where it was solved exactly. In computational geometry, it's been solved exactly using something called the continuous Dijkstra paradigm. These are really cool techniques. But what's unfortunate, perhaps, about them is that they all involve pre-processing, and they all involve additional memory overheads to store the special data structures they compute. And if the map changes in any way, everything gets thrown away, and you have to start again. So one of the interesting application areas that we're thinking with this work is video games. And video game developers have been thinking about this problem for a while as well. What they do is they compute a path on the grid, and then they do something called string pulling, which is exactly what it sounds like. You just pull the path taut as part of a post-processing step. So there's been a number of works in the artificial intelligence community trying to improve the basic naive string pulling idea. So theta star is a typical example. Also blockade star. You can think of these, loosely speaking, algorithms as doing string pulling, but during the online search phase rather than as a post-processing step. So string pulling, theta star, blockade star, they're all online, but unfortunately they only compute approximately shortest paths. So at the time that we submitted this paper, we thought that nobody had managed to solve optimally and online any-angle pathfinding, and one of our reviewers pointed out that, well, there was a paper in a workshop a few years ago where the authors claim that they've done it. I say claim because although they provide lots of nice empirical results, they don't provide an explicit proof. Maybe they thought it was not necessary. I don't know. What's interesting about this method called accelerated A-star is that it's basically doing some variation. You can think of it as string pulling, but what they do is instead of comparing, so when you're relaxing a node, instead of comparing against a single parent, they compare against everything on closed. So the longer the path, the longer an expansion takes. Okay, so what we do is we have a method which has none of these disadvantages. It's called ANYA. It's provably optimal, and I thought I'd give you an intuition as to how it works by way of a small example. So normally you expand nodes one at a time. What we want to do is expand sets of states together at the same time. So we represent the set as an interval, and from each interval we choose a representative point, and we use that to compute a lower bound on the cost to go. So how does it work? Well, we have a starting location down the bottom, a target up the top, and if we expand the start, we might generate an interval such as this blue line, okay? And intervals beget other intervals, which beget other intervals. until something interesting happens. We try to generate an interval where not every point in the interval is visible from where we started. Okay? And so the reason this is interesting is because the visibility changes, right? So all of the points that are blue are visible, but all the points that are orange are not. And what we do is we chop the interval, and we say forevermore, to reach any of the points in the orange interval, you have to turn at this orange turning point. So the search continues, and now we expand successor states of the orange interval, and we continue until we get to another point again where the visibility changes. And we remember forevermore that in order to reach the points in the green interval, we have to turn at this green point. And we continue until we get to the goal. That's the intuition. So how does it actually work concretely? So a search node in our algorithm is simply a tuple. It's a combination of an interval with a root node. So the interval is simply a set of contiguous points that are all visible from the root. And the root is simply the last turning point on the way to this interval. Okay? We treat the start node as a point interval with a special root that's located off the map. That's it. It's really simple. So, okay, given this kind of unusual search node, how do you generate a successor? It's also very easy. So simply what we want to do is we find a successor by traveling from the root of a node through its interval and to a point either on the same row as the interval or on the next row. Okay, only one row at a time. So, for example, there's two kinds of successors. We distinguish between observable successors and non-observable. So, for example, this node here, IR, has two observable successors, I1R and I2R. Please notice all the points in I1 and I2 are visible from R. The reason it's not a single interval is because there is in the middle this corner point, and we saw before that these are interesting points where the path can turn, so we chop the interval whenever we have one of these points in the interior. We also have non-observable intervals. So here we can go from R through I and get to I3, which is a different interval, but which is not visible from R. We can also get to I4, which is not visible from R. So for both of these intervals, when we generate these as successors, we give them a root R prime because we have to turn there in order to reach those points. So, okay, we've got nodes, we've got successors. How do we search? What we do is we say for every interval, we're going to choose the point P that has minimum F value. And, okay, so you might think, well, there's lots of points in an interval. How are you going to do that? We don't want to check them all. It turns out it's very easy, and I will argue this just by showing you all the cases that could possibly happen. It's just a small number. So the first case is when the goal is located somewhere such that the straight line from the root to the goal passes straight through the interval. Then we can just do an intersection test, and we can find easily the point in the interval that minimizes F. Sometimes the goal might be such that it's above the interval, but the straight line doesn't go through the interval. In this case, we can choose the endpoint of the interval as the point that minimizes F. Sometimes it might be on the same line as the interval, on the same row. And again, we can choose another endpoint of the interval and find the point with minimum F. Sometimes the goal might be below the interval. So what do we do now? Well, simply we mirror the goal through the interval, and we get an alternative goal. And it's really easy to show that the distance to this mirrored goal is exactly the same as the distance to the original goal, and we have, again, a minimum F value point. So a couple of theoretical results. I won't really go through them. Please don't read them. The first one just talks about completeness. What it says is that if we expand exhaustively the entire search tree of all reachable points, we're guaranteed to have the optimal path in that search tree if the path exists. We prove this by induction, just basically using the fact that every point belongs to an interval and every interval is visible from some successor. The second result has to do with optimality, and it uses the previous definition. Basically what we show is that we always find the minimum F value point, and successors have F values that are monotonically increasing. So to wrap up, this is Anya. It's a new method for solving the any-angle pathfinding problem. It's optimal, it's online, it has some nice advantages. For example, if the graph changes, you don't have to do reprocessing, but you can keep optimality. It uses some very simple principles. I'm going to do some conjecturing here and say that it's efficient in practice. We haven't implemented it yet, it's one of our future works. But why do we think this? So first of all, hopefully I've convinced you intervals are easy to identify. Also, instead of expanding individual nodes, we expand sets of nodes. Also, our worst case branching factor is only linear in the number of intervals that can appear along a row. So compare this, for example, with visibility graphs, which are quadratic in the size of the graph, or compare it with accelerated A star, which I mentioned at the beginning, which has to consider all the nodes on closed. So some future work, obviously an implementation, and we have some ideas for pruning enhancements. That's my talk.